Hello guys, welcome to another video. I know it's been a while I posted videos on my YouTube channel. Well, it's because I've been busy. I wanted to finish some stuff before the next semester begins, which I've almost finished, so kudos to me, I guess. Well, today we'll be entering a new topic, which is called coordinate geometry. Now, what comes to your mind when you hear the word coordinate? What do you think of? What do you imagine when someone says, "Where are you?" I mean, well, if both of you are mathematicians or scientists, well, and someone asks you, like, "Where are you? What's your coordinate?" The person might be asking you, "What's your position relative to me?" Or, where you consider yourself to be a special person at a rest, a reference frame, or reference point that's not moving. Or some generic reference points where everyone determines the position from. Now, there's some drawbacks of coordinate geometry. Really, I should put in parentheses or brackets coordinate geometry, which is Euclidean space geometry. Euclidean space geometry. Well, it's Euclidean space geometry because most of the things we do in day-to-day life activities, we use Euclidean space, especially in mechanics, classical mechanics. That's the mechanics brought by Newton. Most of the derivatives we take are with respect to time. Time is seen as as absolute. It doesn't change. It's not a dimension. But when you want to start doing relativistic physics, you have to keep Euclidean space geometry aside and start dealing with near space-time coordinates where time is a special dimension. But that's not what we're doing. Today we're going to start doing coordinate geometry. Now, first things first, terminologies. What are the terminologies we use? We use terminologies like coordinates. It's right there, coordinates. We use words like, well, first of all, before I continue with terminologies, I'll be doing, I have to say this, I don't know if I'm going to do coordinate geometry or Euclidean space. Get used to the fact that I call Euclidean space geometry. I'm not too sure if I'm going to be doing Euclidean space geometry for 3 dimensions. I'm not too sure. It depends on how fast I finish this topic. It's not a volatile topic. It's just straight to the point. So I probably will do 3 dimensions if I'm done. It's just when you start going to 3 dimensions, you can't help yourself then to go into other things like spherical coordinates and what's it called? Spherical coordinates, Cartesian coordinates, and rectangular coordinates. Okay, so terminology, as I was talking about before. So we have terminology such as coordinates, point. What's a point? What else? I think those are the 2 main things you need to know for now. What are the definitions? Well, a coordinate is a set of points. A point is just what makes up, just like vice versa or inverses of each other. A coordinate is made up of y, abscissa, I don't know what is it. I'm not too sure if it's the x that's called, I think the y is called the ordinate and the x point is called the abscissa. I'm not too sure, one or the other one. I'm not too sure, but it's not relevant to knowing what, understanding coordinate geometry. Now, as I said before, coordinate geometry is the geometry in space that deals with positions, relative positions, or absolute positions. When I say relative positions, it might be relative to someone or something, or absolute, which is with respect to a generic reference frame or reference point. For Euclidean space geometry, we'll be doing absolute coordinates. That is, all coordinates or all points or all distances or all positions will be measured from the origin. This is, I don't want to start putting numbers, but just know that this is called the y, this is called the x. And then say you have a point in 2-dimensional space. Well, we'll be dealing with the Euclidean space geometry in the universe or in the world of flatlanders. What I mean by flatlanders is a universe that's 2-dimensional and not hyperdimensional, like 3-dimensional and Yeah, so that's what we're dealing with, and afterwards you might be asking what's the relevance of doing two dimensions when we live in two dimensions. Well, as you go to see, you'll see that's actually very very useful. That's how this Pythagoras theorem is. It's heavily used in coordinate geometry for knowing the distance between 2 points. Um, and well, most of the things we do, like if I'm that's why Euclidean space geometry is very useful in day-to-day life activities. If you want to know the distance between me and some, arbitrary person that's standing there, we can't start talking about space-time, time-like separation or something, all this relativistic stuff. We have to talk about Euclidean space because we're not talking about an event. If we start talking about events and trying to know, say, the distance between someone who's standing and someone who's moving, then you have to, drop Euclidean geometry. I start talking about four vectors and so on and so forth, but that's not relevant to this topic. Here we're talking about just distances. As I was saying, if you want to find the distance between me and some hypothetical person in this room, you just have to know from what position. You might say, for the sake of making everything easy, just call the other person your reference point. That will be relative position. That'll be relative position. That's with respect to him. Or if there is, in this case, there can't be any absolute. There can't be any absolute. This is the funny thing. There can't be any absolute reference point. A reference point can be anything. But this is the funny thing. Whatever the reference point is, wherever the reference point is, you remember what I said before, it's relative position because it's relative to something else. Wherever it is, every observer, everyone that actually measures distance between me and some arbitrary person in which you're both stagnant, that is, you're not moving, is going to measure the distance between both of us to be constant. It's not going to change for anyone. Length, distance between both of us, it doesn't change. So that's a lot of talking. Let's just get into the mathematics. So yeah, coordinate geometry. So that's a point, has an x. Let's start doing it. Let me start building it up. So if I have some point x1, y1, that's a point. That's someone that's in this room, right? This is some reference point, some reference view. And I'm somewhere here doing my YouTube video. And this is a point x2, y2. Now I want to know the distance between me and this person with respect to this point 0, 0, that's the origin. I've just got to draw some lines, don't I? Like, draw this horizontal line. This line is referred to as a change in x. That's the displacement of the x-axis. You can see that in this horizontal line that I drew, that there is no change, there is no displacement in y. Therefore, at this point is x2, y1, right? Isn't it? That's what that point is. And I will show you where the Pythagoras. It's pretty simple. I guess some people have already figured what I'm trying to do. So that's what this point. This point is the displacement in the x-axis, and this point is the displacement in the y-axis. So we know what this point is. What the Pythagoras theorem tells us is that, let's call this displacement, I don't want to use the word vector yet. So let's call this distance to be AB, or just A for sake of simplicity. Now, Pythagoras' theorem tells us that A squared is equal to B squared plus C squared. I mean, it's normally reverse. It's normally, you know what? Let me just make it simple. Call this C. Where's my duster? So it can look more familiar. So A squared plus B squared well, this Pythagoras theorem is actually derived from the cosine rule. Well, I want to make a quick, it's not useful, quick, derailing here. When I say Pythagoras' theorem, what does that even mean? What is a theorem? A theorem is something that's not evident. It's not obvious that it's there. Like, that's what you call a theorem. Like, how is it in charges that says that the sum of charges in any Gaussian surface is always 1 divided by epsilon naught. That's 8.854 times 10 to the negative 12. I'm not too sure if that's the correct law, but something like that. It's a theorem. So a theorem is something that's not obvious. In this case, it says that the length of a squared, this is a, b, the squared of the length of the displacement of x plus the squared of the length of the displacement y is equal to the square of the distance between the point P, Q, right? Yeah, so that's a theorem. It'll make more sense because I know the hypotenuse is the longest side of this triangle. If I said I'm not too, but let's say before Pythagoras, someone asked me to estimate what's the length of the hypotenuse, I was like, okay, so it's not always the case that this part and this part are equal in length. That is that A is equal to B. It might be that A can be a bit longer than B and so on and so forth. But I just want to estimate what's going to be the length of C without Pythagoras even figuring out what his theorem is going to be. I could have said that maybe C, or maybe A plus, let's see, perhaps 75%, say 25%, maybe plus 1/4 of B is equal to C. That's probably a rough estimate. That's the whole of A plus 25% of B will be equal to C. Maybe. It seems more, what's the word? It seems more, not obvious. It seems more logically true that the whole of A plus maybe 25% or maybe a percentage is smaller of B is equal to the length of C, but well, that's not actually true. Well, it might be, I don't know if it's true. I may have found a theorem. So yeah, but that's what a theorem is. It's something that's not evident to most people or to everyone in general. So it says a squared plus b squared is equal to c squared. Now what's a squared? A squared is change in x. A is equal to change in x. B is equal to the change in y. So I say that change in x squared plus change in y squared is equal to c squared. Or the length c is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Well, this is what I used to do before. Anytime I learn a new topic, I try to just extrapolate every single term of a formula or of a formula that's always written. So I could have said maybe x2 minus x1 squared is equal to x1 plus x2, x1, x2 minus x1 is x1 plus. The thing about addition is that it's, commutative, I think, or is associative? I think associative is related to parentheses and multiplication. I think it's commutative, so you can always switch the place. X1 plus x2 is always equal to x2 plus x1. But for the algebraic operation, which is called the difference, or which is called minus, the minus sign, it's quite not always the case. So you can't say x1 minus x2. It simply makes x2 minus x1. So x2 minus x1. Well, it's not really necessary that you do this. It's just for the fun of math. Well, these days, doing things like this really even bore me. But like before, I used to be like, if a term is written in some kind of way, I'd always want to write it in a more explicit way. I don't know, for the sake of, I don't know. It was fun to me that time, but now writing this whole thing really, really kills me. I just prefer to write this delta x and this delta y. So, yeah, and let me think of more things I could add to this. So I have changed x. Well, also notice one thing, that the change in x normally it's equal to x2 minus x1, right? But it's not just x2 minus x1, is it? It's also, look, so delta x is equal to x2 minus x1, x2 minus x1. Oh, let me write it like this. So a big ass bracket, x2 minus x1 plus y1 minus y1 all squared. But it's not necessary to write this because, well, why would you write it? While delta y is equal to a big bracket x2 minus x2 plus y2 minus y1 squared. I don't know if you can notice it. So a b is equal to delta y. This x2 and x2 is the same, so you can't, if you do x2 minus x2 is the same thing. While this is delta x. So yeah, that's that for that. So here you get to plug in numbers, which really bore me. Well, you can do some arithmetic on your own. Say, what's the distance between the origin, and that's 0, 0, and some point 5, 5, 3, 2, or what's the distance between the origin and a point on the x-axis? That's pretty interesting. So what's the distance between the origin and a point on the x-axis? In that case, y will be 0 because it's a point on the x-axis. And that's what one-dimensional creatures are going to measure. So if you're living in one dimension, that's only length, you could only measure one number, which is x or y-axis. In this case, let's just call it the x for the sake of simplicity. So that's that for that. What else can I do? Thinking of what else can I possibly do? So one caveat I have to mention is, so when I said it's called Euclidean space geometry, we can't. I know in physics we normally do position time graphs and so on and so forth, but that's like treating time as an absolute. That's something just like doing the y dx or doing the same thing for dx dt, things like that. So for Euclidean space geometry, it's mainly about knowing things in space without knowing the time. It doesn't include time. So that's why most of mechanics is built heavily on Euclidean space geometry. Yeah, so that's that on that. So let me just write everything. Oh, the board just moved. Let me just write that's what I normally do. So this is important thing you should all know or write down. And also note that A is equal to delta x, B is equal to delta y, and delta x is equal to x2 minus x1. delta y is equal to y2 minus y1. As time progresses, I will show you the difference between delta and it's more or less the same thing. Okay, but when I get there, I'll talk about it. I don't want to talk about it now. So yeah. Yeah, I'm back. So it's I don't want to talk about it now. I'll just talk about the difference between, if I say delta x and dx. Yeah, so well, it's more or less the same thing, but what I was talking about is a differential and a derivative, but we're not doing that now, so you need to know that. So, well, you might know, I don't know. I'll talk about it later. So you have delta x squared plus delta y squared is equal to c squared, which is the length squared, and c is equal to square root well, these are basic things, isn't it? So let's say yeah, that's about it actually. Now we'll start to talk about the idea of a slope. What is a slope? First thing I need to mention is remember our definition of sine, cosine, and tangent. So I said before, but I didn't say it. Mathematics told me to say it. That sine of an angle. Let me start writing these things very discreetly because I need to optimize space. Yeah, so let me draw a line here. Well, it's not a line. Yes, so remember that I told you that sine of any angle is equal to the opposite of a triangle. Say, let's say the angle is here. The opposite divided by the hypotenuse. For, let's see, yeah, that's it. Cosine of that angle is equal to delta x divided by c, right? So that's x. So that's the opposite divided by the hypotenuse, and adjacent divided by hypotenuse as well. So and the tangent is equal to sine to explicitly write it. So I have tan equal to delta y. You see that these two c's cancel once you take this to the top, or bring this to the bottom, all cancel. So you have that tan with an angle is equal to delta y divided by delta x. Now what is this? Two things are drawn from here. You can know the angle that a line makes with the horizontal, which is the x-axis, while knowing the slope. We define delta y, delta x to be the change in y per unit change in x. When I say a particle has a velocity and the speed component of the velocity, because velocity is a vector, the speed component, which is the scalar multiple of the velocity vector, is 5 meters per second. It's moving 5 meters every second. Or if I tell you the acceleration of a particle is 50, what's the word? Meters per second squared? No, sorry, yeah, per second squared. That means it's moving. So if acceleration, well, okay, yeah. So this is the slope. If I tell you that acceleration is equal to 50, sorry, meters per second squared. That means it's moving at a 50 meters per second So every second it's increasing its velocity at 50 meters per second. So every second it decreases by 50 meters per second. Every another second it goes to 100 meters per second, 150, and so on and so forth. So the difference will be the change in y divided by 1 unit of time is known as acceleration. But this is just for the sake of drawing parallels and making analogies. So what the slope is, well, when we get to calculus, we say it's the rate of change of the y-axis. Well, that's what it is actually. It's the rate of change of the y with respect to x. Or for this, in this scenario, let's just call it the rate at which the y, which is the dependent variable, changes per unit of the independent variable. So per unit means 1. So per unit, that's what it is. So we have that the slope, let me write this more pretty. So you have delta y divided by delta x, slope. And tan of the angle that the line makes with the x-axis is equal to m, which is the slope. That's one important fact you should know this. Or you should note, not like this. Note. Yeah. So tan of an angle that the line in space, or in space in this dimension is just in a plane. The line that that these 2 points make, the angle, sorry, that these 2 points makes with the x-axis is the you can get the slope from that angle. So if you knew what the angle was, you can get the slope. If you knew what the slope of the line was, you could get the angle that it makes with the x-axis. You can also, if you knew what the angle made with the x-axis, you know what the angle, let's say, the angle that it makes with the y-axis is phi. You can find what phi is by doing 90 minus theta. That would be phi. So yeah, I don't know if I should stop here for today, because if you know this, you're done. If I say let me just do some examples. Should I do equation of a line now? So if I say what's the slope between these 2 points, say √2 and let's say 1. Come on. And Q, which is 3,2. So Let's change this to 2 to make it easy. Two something. I don't know what the units are. Say two. Let's say, what would that be? Because I've been solely talking about space the whole time. It could be anything. But well, in terms of space, what would it be? So it would be, let's say, 2 meters per. I don't know. I actually don't know what that would be, honestly. So it'll be two units. It's got 2 units because we don't know what we're measuring. That'll be the case. Yeah. And what else do I do? Because the rest you can just plug in numbers for your own sake to, I don't know. So yeah, that's about that. Um, yeah, thank you very much for watching today's video. It's not really that much. After this, maybe I have 1 or 2 videos to do and I'll be done with coordinate geometry. And then we can go into more complicated stuff like binomial theorem. Because for my binomial theorem, I want to go into, I don't know if I can still do it, derive the binomial theorem from the Taylor-Maclaurin series and show, yeah, I don't go from binomial theorem, we're going to complex numbers, and then from there we can start some real stuff. This is still like, I should have done this a while ago. I should have done this a while ago. But yeah, that's all about that. If you can do this, the next thing I have to do is angle between 2 lines, perpendicularity and parallelism of lines. What else? Equation of line, different ways of writing the equation of a line, perpendicular bisector. After that, after perpendicular bisector, I'll be done. Well, after that'll be the last thing I'll do. But if time permits me, well, time will always permit me to be honest. But if I have the urge to, I will do 3-dimensional coordinate geometry. And also, I think I have to do how to transform Cartesian coordinates to polar coordinates and so on and so forth. So yeah, but for the sake of coordinate geometry, the only things we have left to do is parallelism and perpendicularity of lines, equation of different forms of writing the equation of a line, y equal to plus b plus c as a normal way of writing the equation of a line, which is a slope intercept form. What else? And after that, we'll do perpendicular bisector and we'll be done. So it's not too much for coordinate geometry. Maybe after that, I'll talk about how to convert how to do transformations, or it's called a transformation from polar to Cartesian and vice versa, I guess. And then after that, I'll be done going to binomial theorem. Well, thank you for watching today's videos. It was fun making this because it was relatively simpler than the one I did before. Yeah, so thank you. Subscribe, like, share with your friends. Thank you very much. Bye.